Hello, this is FlippedHarber for Algebra 2. In this video we're going to cover section 3.1, using graphs and tables to solve linear systems. Now, our objectives for this lesson are to solve a system of equations by using graphs and tables. We also want to classify systems of equations and determine the number of solutions. Our topics for this lesson include systems of equations, a linear system, consistent, inconsistent, independent, and dependent systems. Now, let's get started by talking about what a linear system is. A linear system is a system of equations, that is, two or more equations that are grouped together that contain only linear equations. Now, these equations are in standard form. Whenever we see the x term plus or minus the y term equals some number, that's what we refer to as standard form. Now, I know that these are linear equations because I don't see any powers or anything special going on with the x or the y. I could solve both of these for y and get slope-intercept form. Now, maybe we'll have to do that, maybe we won't. The types of questions that you're going to see in your homework in this section are to use substitution to determine if the given ordered pair, that is an x comma y point, is an element of the solution set for that system of equations. Basically, if I plug this point in, does it work for both equations? And then we want to use a graph and a table, not just one or the other. We want to use a graph and a table to solve each system. And then we want to learn how to classify each system and determine the number of solutions. There's three possibilities there. Alright, so let's take a look at an example for our homework. It says use substitution to determine if the given ordered pair is an element of the solution set for the system of equations. So they're basically asking, does the point 1 comma 3 work in both equations? Well, the way I'm going to answer that is to plug the point into both equations and see if it works. Now, if it works in both equations, then the pair is in the solution set. It's not that it works in one and not the other, it's got to work in both. So, if I substitute in 1 comma 3, that is, I'm plugging 1 in for x, 3 in for y, I get a true statement for both equations. Plug 1 in for x, 3 in for y, I get negative 8 equals 8 for the first equation. Plug in 1 for x, 3 for y in the second equation, I get 9 on both sides. So I get a true statement for each equation. So this point is a solution of the system. Now, is it the only solution? Well, we'll talk about how to figure that out later. But this point is a solution for this system of equations. So, is this point a solution for this system? That is, does negative 4 comma 1/2 work in both equations? Well, it works in the first equation. You plug in negative 4 for x, 1/2 for y, you get a true statement, 2 equals 2. Substitute it into the second equation and we don't get a true statement. We get negative 4 equals 1. So since the point is not a solution for both equations, it is not a solution of the system. Yes, it works in the first equation, but since it doesn't work in the second equation, it's not a solution for this whole system. Okay, so let's look at the other type of problems that you're going to have to do. Use a graph and a table to solve each system. Check your answer, okay? When they tell you to check your answer, that means that you have to plug back in and do what we just did in the previous two examples. But let's start by graphing these two. Do I need to change them into slope-intercept? Well, it might be nice, it might be easy, but it's not the only way to do it. I could graph the top equation by finding x-intercept and y-intercept. I'd probably go ahead and solve for y in the second one. But if you want to solve for y in both of them, feel free. A lot of people prefer doing that. So if you solve it for y, you get y equals 2/3 x minus 1. Means that I have a y-intercept of negative 1. I have a slope of 2/3. So I go up 2 over 3. up 2 over 3. My second equation, y equals x minus 2, that wasn't nearly as difficult to solve for. I find out that my y-intercept is negative 2. My slope is 1, so I go up 1 over 2, up 1 over 2, up 1 over 2. On the graph, it appears that these two lines cross at the point 3, 1. So I think that 3, 1 is the solution for this system. But the problem doesn't say use a graph to solve this. It says use a graph and a table. So what I want to do is make a table, plug 3, 1 in for both, and choose some points around 3 and 1. So basically, I'm going to make a table for each equation. I'm going to make sure that I include 3 and see if I get out 1. But I also want to plug some other points around. I want to choose some other x values. Now in these two tables that they show, they only chose x values leading up to 3. It might be a good idea to choose a number before and after 3. So we plug them in and we make sure that 3, 1 works for both of them. So since when x equals 3, y equals 1 for both equations, then yes, 3, 1 is the solution to this system. By the way, it's the only solution to this system. Let's try this one. X minus y equals 2. 2y minus 3x equals negative 1. Graphing the two lines, it looks like the lines cross somewhere, maybe by x equals negative 3. What's that y value? Well, that's not a real great graph. I mean, they actually drew this with a calculator and printed it in the book. So, what do we do if we're not quite sure? Well, we make a table. If we plug 3 in to the first equation, we get negative 5. If we plug negative 3 in to the first equation, we get negative 5. When we plug negative 3 into the second equation, we get negative 5. So the solution to this system is negative 3, negative 5. When we plugged in negative 3 in for x, we got the same y value out both times. If we didn't get the same y value out, then we don't have a solution. We've got to get the same y value when we plug in that x value. And that table helps confirm that. In this table, they showed some points before and after negative 3. Now, I don't really expect you to make a table this big. Find your intersection, choose, one number before, one number after. That's fine. I don't need to see a table with 10 entries. Honestly, 3 is enough. Now, when we want to classify linear systems, basically we've got 3 options. Those two lines can intersect in one point. This is what we refer to as a consistent, independent system. Okay, we get an answer and we get exactly one answer. Our second possibility is that the two lines actually create the same line. Our two equations create the same line. Now this is what we refer to as a consistent system because yes, the two equations agree, but it's dependent. Our solution kind of depends on where you're at. There's an infinite number of solutions, so if you want one particular solution, you have to have an x value to get out the y value. Our third and final option is that the two equations create parallel lines. Now, parallel lines don't ever intersect. So that means that there's no solution to this system. Okay? The way to spot that, look for the same slope. Okay, here's our names. Again, when there's one solution, we call it consistent, independent. When the two equations create the same line, it's what we call a consistent, dependent system. And when the two equations create parallel lines, we just refer to the system as inconsistent. So, they're going to ask you to classify systems and determine the number of solutions. So really the way to do this is to try to identify the slope. If I solve each equation for y, get it into slope-intercept form, these two equations have the same slope and the same y-intercept. So these two equations, even though they didn't look like it originally, these two equations create the same line. Well, which one is that? Is that an example of exactly one solution, infinitely many solutions, or no solutions? Well, it's this type of system. The two equations create the exact same line. So, we say that this system is dependent with infinitely many solutions. What about this one? We'll solve for y in both systems. They have the same slope. They both have a slope of -4, but they don't have the same y-intercept. So these are not the same lines. These are two parallel lines. Is it exactly one solution, infinitely many solutions, or no solutions? Well, it's actually an example of this third case. So this system is inconsistent and has no solution. Alright, so we're all done. We've looked at how to substitute in to determine if a point is a solution. We've looked at how to solve a system by using a graph and tables. And we've looked at how to identify how many solutions a system has. So, it's time to get to work. I'll see you in class, and I'll see you in the videos.